Hello and welcome to Chapter 8, Mutually Exclusive Decisions. This chapter is organized in two main parts. The first one is talking about economic life and the associated equivalent uniform annual cost. The goal is to determine what is the optimal number of years we should keep a machine and then replace it. To determine that, we need to take into account two different types of costs of owning an asset, let's say a machine. There are the ownership costs, which is associated with buying it and selling it. And of course, the longer you keep the machine, the lower the cost per year is, because you're basically spreading that cost among more years of ownership. And the other type of cost is the operating and maintenance costs. So the older a machine gets, the higher the likelihood that some parts are going to need to be replaced, and therefore increasing costs of maintaining and operating the machine. Think like a used car, right? The older it gets, the higher the likelihood you need to change the alternator and many other components. So the operating and maintenance costs tend to go up. Therefore, we have two opposing forces. The ownership costs tend to bring the aggregate costs down, but the maintenance costs tend to make the aggregate costs go up. So given these two patterns, where is the global minimum? Where is the addition of annualized operating costs and annualized ownership costs? Where does it reach a minimum? That's the goal. Now, when we are given an exercise, we're going to be given an expected life for the machine, and that's the proxy we're going to use for the maximum number of years we can keep it. And we're going to be given the purchase cost, the selling cost, and the maintenance costs. The goal is to annualize everything, transform that cash flow series into annuities. And we need to pay attention when solving these exercises to computing every single year what is going to be the equivalent uniform cost. So for example, if we keep it 2 years, how much is the cost per year? If we keep it 3 years, how much is the cost per year? So because the longer we keep it, the lower are going to be, up to a certain point, the costs of ownership. And that point being the inflection point, when the summation of the two types of costs starts going up. However, we need to pay attention to cases where, for example, there are multiple minima. We want the global minimum, not a local minimum. So that's why we need to compute the EUAC, the equivalent uniform annual cost, for all the years that we could potentially keep the machine. That is, for all the expected life of the machine, and find the global minimum. So we should not stop at the first inflection point we find. We should compute for all the years of the expected life of the machine, just to make sure we are actually finding the global minimum, because we might end up with some local minimum which is not the solution to the problem. The formula in implicit form is given on page 124. And basically says that the equivalent uniform annual cost, meaning the annuity, it's equal to annualizing the initial costs, so find the annuity given the purchase price, the present value, the interest rate and the number of years, right, we are simulating for. Then we subtract the annualization of the expected salvage value. So we have an estimate for how much we're going to sell it. What matters is how much we actually sell it for. So if we have the number we actually sold it, that's the one we use. If we only have an estimate, a forecasted value, then that's the one we use. If we have both, we use the actual selling price. So this is a future value that is transformed into an annuity, given the interest rate and the number of years we are simulating for. So this component here addresses the ownership costs. They go up with the purchase price and go down with the expected salvage value. And then we add the operating and maintenance costs. This component can take a variety of forms. It can be a linear gradient, that is, something that is increasing by a fixed dollar amount per year. It could be flat annuity, something that is constant every year. Or it could be a geometric gradient, something that is increasing by a percentage rate every year. So whatever form it takes is specific to each exercise. That's why they leave it here in this generalized notation. But this is the key formula behind computing the equivalent uniform annual cost. Now note, you don't do just one computation. For example, if the expected life is 3 years for the machine we are buying, then we need to compute this formula 3 times. One for the case we decide to keep it just 1 year, twice if we decide to keep it for 3 years, and a third time if we decide to keep it for 3 years. Because depending on the number of years we keep it, the annuity, the equivalent uniform annual cost, is going to vary. So conceptually, this is all about the equivalent uniform annual cost and finding the optimal economic life of the machine. Then the second part of the chapter focus on what is known as the incremental analysis or the defender-challenger approach. The interesting part of this section is that rather than focusing on the original cash flows generated by each project, we're going to focus on the differences in cash flows. So we compute the difference, for example, in initial investment and the differences in the expected cash inflows afterwards. And we ask ourselves, is it worth it, the extra investment, in order to obtain that potential extra revenue? If so, then we should go with a more expensive project. If not, then we should stick to the cheaper project. Now, the methodology to compute this follows a 6-step process, as outlined on page 132. And that is, first, you're going to exclude any project that is over budget. Among the options presented to you for investment, those that you don't have money for, you exclude immediately. So reducing the number of alternatives to further assess. Second, we're going to use a decision criteria, being it the net present value or the internal rate of return, on the original cash flows, just to verify if they are worthwhile or not. Given that we have money, budget, to invest on them, now we have to make sure that they actually provide returns and not losses. So once we do this cleansing of the data of the projects, we move to the next step. The third step then is, from those that are economically viable, then let's rank them from the cheapest to the most expensive. Then, step 4, we're going to start the comparisons. We're going to call the defender the cheapest option and the challenger the next least expensive option. So that we ask, is the extra investment worth it? That's what step 5 highlights too. Then whoever wins from this comparison, being it the defender or the challenger in this first comparison, moves on to the next comparison, which is going to be compared. Whoever wins this first round is going to go to a second round against the third least expensive. And whoever wins that round moves on to the next combat, let's say. And this is done till all the options are exhausted and we find the overall winner. In the process, you are able to make a rank of the projects, from the best project to the worst project. So that's what the next pages are alluding to. Please go over example 7. Here says you have a budget of $350, and these are the alternatives you can invest in. So this EX project is $385. We only have $350, so this one is immediately taken out from consideration. Then for the remaining projects, we evaluate if they are economically viable. And here they are saying, for example, pick one of these 3 tools. And by computing net present value, annual worth, and net future value, then we see that the EC project is not worth it. The EX we already excluded. Now the EC is excluded as well, So we are left with projects B, R, D, and S to do further analysis. Once we realize these are all economically viable, the B, R, D, and S, we then rank them based on the initial cost. This is using absolute value methods, and this is using the relative value methods. Either way, you should get the same elimination. And we're going to rank them by initial investment. And that's what this table here at the bottom of page 133 is doing. So the cheapest is project R, it only requires an investment of 100, then S with 200, and D with 220, and B with 300. So our first defender is going to be project R, and our first challenger is going to be project S. Whoever wins this first comparison is then going to be compared with project D, which is going to be the challenger for whoever wins this round. Then whoever wins that second round is going to be compared to project B. And once that comparison is done, we find the overall winner. That's what the next pages are showing. So you see, for example, the first round. The defender is project R, the cheapest, with an 100 investment. The challenger is project S, which requires 200 investment. So is the incremental cash flow, the difference, the extra 100, worth it, the extra 11 in annual revenues? Then we are told which tool to use. In this case, they're starting the evaluation using the BC ratio. So the change in cash flows, that's what the delta is there for. So is this annuity of extra $11 worth the extra investment at time 0 of 100? And the answer is 0.68, right? The present value of this annuity is smaller than 100. Namely, this present value of this annuity would be $68 at 10% over 10 years. So as it's less than 1, we conclude that the defender wins, meaning that the cheapest project is better. It's not worth it to invest the extra 100. So then project S is going to move to the next round to be compared with project D, which was the third least expensive. And the same procedure is repeated regardless of the tool you want to use. For example, internal rate of return, external rate of return, whatever you are told to use. And in this case, using the BC ratio, the extra 120 investment, is it worth it in order to get extra 20 as an annuity over 10 years? And the answer is yes, because the BC ratio is greater than 1. So the defender in this case wins and moves on to the next round to be compared against the most expensive. There's just one project left, project B. So now the defender is D because it's cheaper than B, and we compute again the differences in cash flows. Is it worth it, the extra $80 investment, in order to get an extra $5 annuity? And the answer is no, because the BC ratio is less than 1. The extra benefits do not outweigh the extra cost. So the overall winner is D. D is the best project. There's no other projects to be compared against, and therefore we conclude that D is the best project. So please read the rest of the chapter, but that's the essence of it. Now we're going to move to exercises.